Great, I'll turn on my microphone now, and hopefully everybody can hear me here and also in the land of the internet. Good evening, everyone, and welcome to the August meeting of the Madison Astronomical Society. Before we get started, I first like to welcome everyone here, and I'll be mindful, I gotta be mindful where I'm standing or else I get feedback. This is the first time I've ever really done this. Is kind of a weird kind of arrangement, but we'll do the best that we can. Trying to collect my thoughts. First of all, yeah, I hope everything's working well on YouTube for us. And just to kind of grab everyone's attention first, what we're going to do is we're going to do some announcements first. And then at 7:30, we're going to begin our guest presentation. And then for those of us who are joining us on YouTube, at the end of the presentation, they will have the opportunity to type in their questions if they have any questions or comments that they would like to ask our guest presenter this evening. Also coming up, I guess, we've got some really interesting things coming up in the next couple of months. First off, if any of you are longtime Madison Astronomical Society members, way back in the 60s, 50s, 60s, 70s, and 80s, we used to have an observing site in Fitchburg back when Washburn Observatory used to have actually two observatory buildings. Of course, you had the large observatory building that's there now, and then next to it you had a student observatory, which kind of fell out of use and was going to get torn down kind of in the mid to late 1950s. So then what happens is a fellow in Madison named Oscar Mayer, who was kind of a fan of astronomy, decided, well, you know, that's kind of a bummer to tear down that building. Well, how about if we move it from the current site on the observatory hill down to Fitchburg, where there's some darker skies, and then I'm going to donate this building to Madison Astronomical Society so they can do observing out there and they can hold their meetings out there. Well, so they rededicated that student observatory as the Oscar Mayer Observatory way back when. So when the light pollution kind of got worse and worse in the early 80s, by the late 70s and early 80s, Madison Astronomical Society started entertaining ideas of moving our observing site out to Pine Bluff, and that didn't quite work out. And then a member of the Astronomical Society said, hey, well, we've got some land down in Greene County that we would like to donate some of the land that we own. And that was the Yana family, whose current grandson still owns the property. You might have known him or heard about Carson Yana. Well, his grandfather donated that land, and we moved our observing site to Yana Research Station, which bears the family name. So in the meantime, that observatory, Oscar Mayer Observatory, kind of started falling apart and wasn't put to any use. So Promega, the president of Promega, comes along and says, you know, I would really like to turn this into a valuable, Oscar Mayer Observatory into a valuable community resource. And since over the last several years, they have renovated it and completely redone the building. They had one of our former members, Matt Mills, donated a 16-inch Schmidt-Cassegrain telescope that's currently mounted on there on a very fine, high-quality Paramount that got put in there about 3 years ago, and then, or was it 4 years ago already? And even as we speak now, over the last year, there's been a postdoctoral student there, or a postdoc, pre-doc. There's been some, my memory on the details is kind of fuzzy, but there's actually a UW, I believe, a postdoc person there doing active research using that telescope and observatory these days, which, my long story is getting to this point. Coming up on where is it? Looking at the wrong, bear with me. Coming up on September 7th at 3:30 p.m., that observatory is going to be renamed and rededicated as the Bell Burnell Observatory. And this is, and I'll just read you a little bit about it. This is a naming dedication for the Bell Burnell Observatory and the Special Astronomers Day panel discussion, which is going to be the day before that. And the guest of honor, who the observatory is being renamed for, is Professor Dame Joycelyn Bell Burnell, who is also not only going to attend the rededication ceremony, but also a panel discussion the day before. And some of you might not be familiar with her, but she's the British astronomer who discovered pulsars and also cosmic sources of peculiar radial pulses, which turned out to be pulsars. So, oh yes, Terry?
There's a doctoral student doing some research at that telescope.
Right.
Also.
Yeah, that's what I was just saying a little earlier. Unfortunately, I can't remember his name. But Dr. Bell Burnell is going to be there for the dedication ceremony at 3:30 p.m. on September 7th. And then on the previous day, and that's going to be at 5511 Bjorkston Place in Fitchburg, where the observatory is at. And then at the previous day, on September 6th at 1:30 p.m., there's going to be a panel discussion. So for all of those Madison Astronomical Society members who have gotten announcements recently, there is an RSVP. Everyone's welcome to show up, but there is an RSVP on their website that I handed out the link to, where you can sign up and attend those events, and it's going to be really great. And I encourage everybody who's a member of the society to go. Yes, Terry?
Yes, his name is Bob Alaosi.
Bob?
He's Bob Alaosi, A-L-A-O-S-I. He's a PhD candidate.
So yeah, PhD candidate Bob Alaosi, and I think I met him not that long ago, but it's really great to know that they're using that facility for serious research, and it's just a wonderful building. I encourage anyone to go out there just to see the new observatory building. Yes, Kevin?
I was going to say, if you are not familiar with the guest of honor, you should look up her name and look at the history of what she's done in her life and how she some of her work resulted in a Nobel Prize, but ironically not for her.
Not for her. That's right. And those sorts of things can be touchy subjects, but if you look up on the Encyclopedia Britannica website, they have a very, very good biography for her. So I suggest anyone in the club look up Jocelyn Bell Burnell, Google her name, and read up all about her. Yes, Jürgen?
Yeah, I was just going to say, I remember when that discovery came out in Sky and Telescope, they mentioned her, they in passing mentioned the researchers. So, she got the acclaim at the time, but then she never got a Nobel Prize.
All right, so also coming up in the next month, we are scheduled to have Moon over Monona Terrace on Friday, October 7th. So we're all looking forward to that, and in the past we've done that virtually. So hopefully we get clear skies this year, and we have a lot of fun interacting with the public and exposing the public to astronomy. So that's Friday, October 7th at Monona Terrace. And then on our next event, our next meeting will be here Friday, September 9th at the usual 7 o'clock, where MAS member Jeff Schawlow is going to give a presentation about astronomical software. Does anybody else have any announcements or information that they'd like me to repeat? Or you can come here, I can let you speak into this microphone. Jürgen? Yes, Jürgen?
I'll yell. Yesterday I was out at Picnic Point and leaving there towards dark. And there was a steady stream of people with very long lens cameras walking out there. And I finally asked one of them, "What are you doing?" They said, "Oh, the moon is rising right over the Capitol.
Uh-huh.
And so you might end up seeing pictures from that. And at the same time, they wanted to see the meteor shower.
All right, so
The notion of going out to the tip of Picnic Point and getting a perfect angle over the Capitol as the moon rises.
so when was this then at Picnic Point? Oh, last night?
Yeah.
So I guess, yeah, everybody who might not have heard that last night, I guess there was a perfect alignment from Picnic Point looking at the Capitol where the moon rise was going to be. So you might see some pictures like that on the internet real soon. So that sounds really neat.
I wonder if John Rummel was out there.
I,
That's the type of thing he would do.
yeah,
He would have mentioned it.
yeah. All right, yes, Terry?
Someone wants to know when the Bell Brunel will be available for observing.
I don't know that personally. I know that the Promega and the owner of Promega, Bill Linton, does have plans for public outreach like that in the future. So we'll have to be sure, if we hear something from them about that, we'll be sure to relay the information. But again, yeah, for the rededication, if no one has had the pleasure to go out there and see what they've done with the observatory, this is absolutely the best opportunity to do that and go and see what they've done. All right, I don't know, it looks like everybody I see here is a familiar face. Is there anybody here who's never joined us at Madison Astronomical Society before? The entourage with the guest of honor. And yeah, just to ask you, yes, what's your name, sir?
My name is Rick.
Hi, Rick. Nice to meet you.
Pat Malloy.
Pat Malloy. Nice to meet you. Interested in amateur astronomy at all, or?
Not so much.
It's never too late to get hooked. I'll tell you that. Well, all right. We're getting closer to 7:30, and I don't want to jump in it too soon. I'm going to kind of waste 3 minutes just in case people join us online in the last minute. I don't want to kick things off too quickly. So I guess.
In person since I'm not up the door anymore.
Yeah. And yeah, that's one thing we'll have to do is we'll have to make sure that they know next month that they know that we need to have the door unlocked on the second Friday of every month. For those of you who are online, yes, they were surprised at Space Place that we were coming in here this evening. So our Vice President, Kevin, was kind enough to make sure that everyone was able to get into the door before the meeting started. So yeah, thanks, Kevin.
Other duties as assigned.
Yes, and it's a reminder that anybody in the club that has an idea of something they would really like the club to do, it's always an opportunity to volunteer and make it happen. So, and any idea is a good idea, even if it's not a feasible idea. Yes, sir.
Could you just give an update on the status of the Yana updating?
Oh, the upgrading?
Yeah.
Yeah, I think we've got a pretty idea of where we'd like to put the pads in and everything, and it'll be just a matter of putting together a presentation that we can share to all the members, because of course, like with the last fall when we upgraded the electrical service, we expect everything to be well in excess of what the board can have for discretionary spending for a single thing. So we're going to have a formal club meeting, discussion, and a vote on how to proceed on that when the package is all together.
The board also had a very busy spring and summer with other matters. So
Yes.
Kind of got put a little bit on the back burner, but probably going to be our biggest priority going into the fall.
Oh, yes, Terry?
Just a reminder that when there's somebody out here speaking, could you repeat what they're saying?
Yeah,
Because
as best as I can, but yeah, and I try to kind of reiterate it. Yeah, for those of you, yeah, we were talking about draft plans for renovating Yana Research Station in particular, adding concrete pads and upgrading all the electrical work. And yeah, some of you may have followed the club that we were kind of distracted by learning how MAS can contact lawyers to have certain services rendered in tricky situations, which we were able to manage this year. So we thank everyone for their patience. All right, I think it's just about time to start the main event here. Tonight we have a very special guest presenter, and the topic is stellar spectroscopy and the formation of chemical elements. And I know there are some chemistry buffs in the club like myself that are going to especially enjoy this presentation tonight. And I take great pleasure in presenting to everyone Dr. Jim Lawler from the UW Madison Department of Physics. And he was the Arthur and Aurelia Schawlow professor here at UW Madison. Just to tell you a little about him, he just recently retired in May of this year. Prior to retiring, he was the Arthur and Aurelia Schawlow Professor of Physics at UW Madison. He spent his career in atomic, molecular, and optical physics with a focus on developing and applying laser spectroscopic techniques to determine accurate, absolute atomic transition probabilities. Lawler received his MS in 1974 and his PhD in 1978 from UW Madison Physics Department, studying with the now Professor Emeritus Wilmer Anderson. In the 2 years after earning his doctorate, he was a research associate at Stanford University and then returned to good old UW Madison as an assistant professor in 1980. Lawler has accumulated numerous awards and honors over his distinguished career. He is a fellow at the American Physical Society, the Optical Society of America, the UK Institute of Physics, and in 2020 he was elected to as a legacy fellow in the inaugural class of the American Astronomical Society Fellows. He won the 1992 W.P. Alice Prize of the American Physical Society and the 1995 Penning Award from the International Union of Pure and Applied Physics for research in plasma physics, the two highest national and international awards in the field of low-temperature plasma physics. In 2017, he won the here I go with my fake, phony British dialect. I wanted to say laboratory. He won the Laboratory Astrophysics Prize of the American Astronomical Society for Research in Spectroscopy. Ladies and gentlemen of the Society, I kindly and gratefully present to you Dr. Jim Lawler.
Thank you. Thank you for the kind invitation, and thank you for the introduction.
You're most welcome.
Okay. I'm going to have to sit down, but that slows me down. So that will work fine, I think. Now, why doesn't it go on? Press. Oh.
If your monitor's asleep, it might not be getting a signal.
I think it's working now. Okay.
There we go.
There we go. There we go. Stellar spectroscopy really teaches how stars make most chemical elements. Now, I'm going to go through a few minutes of things that some of you already know, but that's okay. You shouldn't underestimate how much people enjoy hearing what they already know. Science has really changed a lot, even during my career, and the lone wolves, there's far fewer of them now. Most teams have many, many members. So particle physics is two big detectors on opposite sides of the Large Hadron Collider. That's it. And each paper comes out sort of per day with 500 authors, or 1,000 or 2,000 authors. And health problems like I'm having right now of a team member are much less important because people work in big teams. Society's putting pressure on science. Everybody wants a state-of-the-art experiment on the cutting edge, and they're expensive, they're big. They're $1 billion or more per experiment. And so you have fewer experiments. This is just the way science is going. It's I gave examples: a Large Hadronic Collider, the International Thermonuclear Experimental Reactor, 50-meter telescopes, X-ray free electron lasers for structural biology, FRIB. They're all in the $1 billion scale, and you can't build that many of them. You just can't. So society expects more from us that way. Now, stars made most isotopes. There's a few of them that we label as primordial. There'll be hydrogen, deuterium, and helium, and helium-4, and traces of lithium and beryllium, and everything else has to be made in stars. So these were from the beginning, from the Big Bang, when those elements, or those isotopes were made. Well, everyone knows space is big, and we'll put some numbers in. Light speed is the speed limit. You're not going to change that. And special relativity is right. We've looked at it a lot of times. Now, science fiction writers invent warp drive to keep the plot going because they want the antagonist and the protagonist to interact, not with the great-great-great-great-grandchildren of one of the of either the protagonist or of her travels. They want them to interact directly with each other, so we have to have warp drive for that. But there is no evidence to support it, that anything goes faster than light. There was a brief claim from one of the LHC collaborations about neutrinos going faster than light, and there's a big fight inside the collaboration over a publication of it. And what happened in the end was they went public, but then they found the loose fiber optic connector. And they're faster than light, neutrinos went away. Anyway, we'll put some numbers in as we go along, but space is very big. Now, absorption spectroscopy, the wavelength, or the color, if you will, tells us which atom ion we're seeing. And we need something else to say how much we're seeing. We need the strength of the interaction of light and atomic or ionic resonance. And astronomers like to have a dimensionless decay rate, a log GF. It's directly proportional to the decay rate. So they treat each atomic resonance as a simple harmonic oscillator when they do this. And that's the way we work. We need some way to quantify the interaction of the light with the atom or ion. Well, fusion makes some elements, some isotopes, but only up to iron. And in reaction, switches from exothermic, where it spontaneously releases energy, to endothermic, where it absorbs energy, and fusion turns off. So everything else is made by neutrons. This has been known for a while. There's a rapid process. There's a blast of free neutrons that overwhelms all the decay process. And we were wondering what that was. For a long time, people were thinking it might be a core collapse supernova. And I've had, given talks where people have come up to afterwards, including the chief scientist on the Hubble telescope, and said, we're pretty sure it was core collapse. Well, now they're pretty sure it isn't. They think that it's neutron star mergers. It's definitely one of the sites. But peculiar early supernova might have been important too. And then there's a slow process where the free neutrons are overwhelmed by the decay process, and that's an asymptotic giant branch stars. We knew that about the slow process right away because Merrill discovered technetium in a star. He saw it spectroscopically. And since its longest lived isotope is around 200,000 years, that's pretty short for stellar evolution. It was made there. And so that told them right away that something was happening in asymptotic giant branch stars That was a long time ago. Now, some of you knew these things already. The near infrared is going to be a lot more important in the future than it is now, because the mercury cad telluride, or Hawaii detector arrays, that's your nickname, it was invented in Hawaii, make them infrared CCDs, and so dust is more transparent at longer wavelengths. And they're at the heart of the James Webb Space Telescope, these infrared arrays. Now, what's happened, of course, is that there isn't the consumer applications that drive down the price. The consumer applications for CCDs really, for visible detection, really drove down the price. But for these infrared detectors, they're still kind of pricey. You can easily spend $500,000 on one of these detector arrays. There are windows in the infrared from the ground, and Apogee works in the H-band. It looks at old stars and the galactic balls for the first time. We hadn't been able to see those before. And there are rare Earth lines showing up to approximately the same energy of 6s, 6p, 5d, and 4f electrons. Well, isotopic structure and hyperfine structure is better resolved in the infrared. And each star has a different mix of isotopes. It depends on the nucleosynthetic history of the material that made up the star. So it can have different. So the infrared is going to be very important, 1 to 2.5 microns in near infrared in the future as these detectors become more and more widely used. For the work at Wisconsin, there were two key pieces of technology. You can look back over a multi-decade career, and I can pick them out. The tunable lasers really made a big difference. And the same dyes, chemical dyes that color your clothes and your food, can be made to laze. And it's broadly tunable. You dissolve the dye powder in a common organic solvent, like ethanol or methanol or something like that. Peter Sorokin was at IBM, and he was in the USA. He's originally from Russia. And he got a dye working, a dye laser. And Schaefer and his colleagues, who were more or less, they also got dye laser working about the same time, more or less at the same time. So who really invented the dye laser, Sorokin or Schaefer? Well, it depends on whether you're American or German. And then you decide who invented it. The tunable dye laser was invented by Ted Hinch in 1972. He was one of my postdoctoral mentors. He and Schawlow both won Nobel Prizes different times. What we did at Wisconsin was develop a way to make beams of everything, the whole periodic table, from the top to the bottom. We could make both atom and ion beams, and we could make beams of iron, cobalt, even tungsten, as easily as other people made alkali beams. And that gave us a big edge as we went forward. Now, I'm glancing over at your clock. I want to, let me go back one. If I have time, I want to talk about the hot part of AMO physics. There's an infinite amount of funding available, and it's all about quantum information. And it affects security of the internet and the World Wide Web. And so people want to understand this. If you put your credit card number in, and you're buying something from Amazon or wherever, you don't want extra charges to start piling up on your credit card. And so it is encrypted when it goes. And I'll if I have time, I'll say a little bit how it works and give you some of the history of the quantum information area. Okay, so those are the things I'll be talking about. This is a famous plot, periodic table from Jennifer Johnson at Ohio State. And we worked together on different things over the years. And she has a drawing here of how things were made. And you see right over the top, there's Big Bang fusion, where you made hydrogen, both isotopes, Z equal 1. You made helium, and a little trace of lithium and beryllium. Now, for Big Bang cosmology, there are three pieces of evidence, and one of the three is, one of the triad of evidence is this abundance of hydrogen helium isotopes. So that was very important in the development of Big Bang models. The Hubble recession, expansion of the universe, is another one, and the 3-degree background radiation is the third piece of evidence for the Big Bang cosmology. So we're making a lot of these elements toward the bottom of the periodic table with, let me see if I have a pointers here somewhere. I think I lost it. We're making a lot of these with neutron capture. Oops, I seem to have lost a laser somewhere. Oh. Uh-oh. There we go. We're back. Toward the bottom there, you see elements that are made via neutron capture. There's a little bit of another way to picture this. This is fusion. Now, hydrogen can burn for billions of years, and by the time you get to the bottom in a massive star, you end up burning silicon for like 1 Earth day via fusion, and then the core collapses. So it really changes as you go to heavier elements. Okay, so we have the elements and isotopes that are primordial right at the top, hydrogen, helium, and then we have those made by fusion that are in black, and the yellow is the neutron capture elements. So those are the elements that is most of the periodic table, and we didn't really know where they were being made, some of them, until this neutron star merger was seen by the LIGO-Virgo collaboration. We had no really good sites, so that was a big discovery for us. Now let's talk about the size of the galaxy and the size of the universe. You can launch something with a chemical rocket and use gravity to speed it up. And so the speed record for a chemical rocket, which is a technology we know, is now held, as of last week, by this Parker Solar Probe. It's falling into the sun. So it's going 100 miles in a second. It's pretty fast. It's 163 kilometers a second. That's about 100 miles a second. And the nearest star outside the solar system, obviously the sun's a star, is about 4.25 light years away. Proxima Centauri, it's a binary system, Alpha Centauri and Proxima Centauri. And a probe can get there in 7,822 years using the Parker speed as of last week. There's a way to do this gravitational effect at speeding things up where you can go by planets and do it. But the Parker probe is actually falling into the gravitational well of the sun. Well, 7,822 years is sort of the age of civilization. If you go back 8,000 years, people are really just beginning civilization. Now, if you talk about crossing the whole galaxy, you're talking about timescales for human evolution. You're talking about 100,000 light years, and so you're talking about really, really long times to get across. So the galaxy is big, and the universe is much bigger. But a galaxy alone is enormous. So how does absorption spectroscopy work? Well, pretty much the same, whether you're an analytical chemist or an astronomer or physicist. You have a continuum source and an absorbing sample, and then you see a little absorption line. Astronomer would have a telescope and a spectrometer. They see a little absorption line, and the wavelength or the color tells them what atom or ion they're looking at. But to say how much, you really need something more. You need to know the strength of the interaction of light of a particular color with the atom or ion that you're interested in studying. So absorption spectroscopy is pretty much the same for everybody. Now, stars have a temperature gradient. So the center of the star is where there's the highest pressure, where it's hottest. And the part you see, the photosphere, is coolest and the lowest pressure. It's just the edge of the star. And real photospheric models do not have a step boundary. The temperatures are modeled using radiation transport equations. But it's still absorption spectroscopy. It's very much like everybody uses. The chemists talk about Beer's law and so forth. We have a different name for it. More of a physicist's name than the chemist's name, but it's still absorption spectroscopy. Everybody's doing the same thing. So, Fraunhofer, okay, he wasn't the first one to see absorption lines. There's a William Hyde Wollaston who preceded him, but he stayed at it. Fraunhofer stayed at it. So this is the spectrum of the sun as seen with the prism. And he gave names to the most prominent lines, and he just named them after letters of the alphabet. This was in the early 1800s, A, B, C, D, E, F, G. And then over some period of time, they were gradually associated with particular atoms and ions that were being made in the star. But Fraunhofer is the name that everybody remembers rather than Wollaston. Wollaston has a prism named after him. He didn't stay with it. He kind of lost interest in it. And Fraunhofer spent his whole career on these solar absorption lines. And they ended up being called Fraunhofer lines. Okay, so S process, the beta decays can occur between successive neutron captures, and that's the AGB star, and technetium is a proof. And the R process is a rapid, short blast of neutrons that temporarily overwhelms the decay rate. And the neutron star mergers are, I think that's, when you tear a neutron star apart in a collision, you end up with some concentration of free neutrons, and you can make anything. So that's definitely a site, but there may be other sites. And so our S process elements are just ones whose origin in solar system material was dominated by one or the other process. That's all. Those are the definitions that we use. So if you have the R process, you have I don't have my laser pointer, I lost it somewhere. But if you have the R process, you have a blast of free neutrons coming up from the lower right, and you can drive nucleosynthesis elements. They become heavier and heavier, and you go right up a periodic table where you have neutrons on one axis and protons on another axis, and you make isotopes when you blast in neutrons. So there are some isotopes which are sort of hanging out by themselves, and they end up being pure R process. In the S process, you stay closer to this valley of stability, but and there's a P process too, but that's only like 0.1% of the heavy elements. We see mostly R process and S process, a 50-50 split. Well, one of the things you see are metal poor MP stars, and they have similar spectra, and they're sometimes rich in neutron capture elements. So the metal poor stars are the ones that we look for, and we see those, and we can understand more about their spectra. You can't even tell where the continuum is when you go to the sun at some wavelengths. There's just so many absorption lines, mostly iron, just different stages of ionization, that you can't tell what you have. But in these metal poor stars, you can see rare earths, and the rare earths are nice because you can see them from the ground. We like being able to see them from the ground. And so there's a lot of applications to these additives in optical electronics and so forth. So people put the additives into fibers and things to make different products. Some of them military, but some of them civilian products. Okay, the area of an absorption feature has units of wavelength. Let me see if I can just do this with touching it. No.
You can use your
What happened to that?
mouse pointer.
Yeah, what happened to that?
Just use the pointer on the laptop.
Oh, okay.
Mouse.
Yes. There it is. Yeah. There it is. Okay. So it has units, equivalent width has units of wavelength there. And it gives you the column density that you have, a ratio of degeneracies. This is a spontaneous decay rate in Einstein A. This is the speed of light. That's an 8 pi. And this A has been the problem. And the wavelength or color really identifies the atom or ion that we're looking at more than anything else. Now, what we did over 40-odd years is develop and apply new methods for measuring those transition probabilities. You needed to have those to quantify your information, and we hammered on the systematics and controlled the systematic uncertainties, and we had to do it efficiently and cheaply because there was not a huge amount of money available. So in most cases, the wavelengths were well enough known, but the strength of the interaction of the radiation was the unknown that we really worked on with lasers. The wavelengths were measured with large spectrographs in earlier times. In the first half of the 20th century, they were measured with very large spectrographs. Now, all of our transition probabilities are normalized with radiative light transfer laser-induced fluorescence experiment, and that made them accurate and precise to within a few percent. They were very good, and what gave us the edge was we made a atom-ion beam source that would work with the whole periodic table, and that gave us a real edge over the competition. SRC gave us our own beamline inside it for 2 weeks for 25 years. That was very nice. We had to put a spectrograph on it, but that wasn't a problem. And of course, collaborators who were modelers and real observers, Chris Seaton and John Cowan. They're still active and doing some things, although both have since retired. And Chris and John gave us an edge because they suggested the most important atoms and ions, and they taught us some astrophysics. And the rare earths were really nice and accessible to ground-based observations. And europium is primarily an R process element, and was priority number 1. Lanthanum is primarily S process element, and was priority number 2. And the weak UV ion lines with low excitation potential for the ion groups are very, very important because we'll say more about that. There are lines which are highly reliable. So what are our key challenges? Well, mapping the galactic chemical evolution. How did it really change as time went by? And we want to understand the limits of 1D LTE models. LTE is local thermodynamic equilibrium, and 1D is one dimension. And the reason people use those models is because that's what they knew. They didn't have an infinite number of rate equations, which were reliable and accurate. So they only had a few rate constants, and they did a lot of these one dimension local thermodynamic equilibrium models. And we're still kind of uncertain on this, whether or not there's more than one R process site. So there's a debate over that right now, whether or not some of the early supernovae might have done it. People are working on it. So when we look at a transition probability, if a given upper level can decay to let's say these 4 lower levels, we have these different color lines. Measuring this total decay rate of that level, that upper level, that total decay rate, that lifetime, gives you the summation of these A coefficients. And you do a tiny bit of algebra, and you end up with this being your whole normalization. If you have this lifetime, you have it. You have your normalization, you have it right. You have it to a few percent. And so you can make relative measurements and then combine them with the lifetime, and you get absolute A coefficients to go forward with your work. So we had a couple of machines like this. We could make, it was a poorly collimated beam. It didn't matter. We could just shine the laser through the beam, and we can make beams of everything. And what's going on here is that this is hollow cathode plasma, so that we don't have to melt tungsten. We can sputter tungsten into gas phase, or we don't have to melt things. We can sputter them, and so this is an example of decay data. This is a barium trace, 2,528 or something. There's enough information there to set up the exact experiment. Everything's been printed out. So the lower trace with a little ring, that subtracts away, by the way, is when you tune off the line, and the upper trace is when you tune on the line. And you measure lifetimes to a few percent with this apparatus. We've printed a lot of things out as we went along, and we put them in books so that people could go set up the same experiment and try to reproduce it within error bars. This entire sweep is the time window is 50 nanoseconds. So this is a transit digitizer recording that we took. But we would take these with 640 laser shots to get a lifetime, and it worked well. So we could work with metallic and non-metallic elements, and we would just introduce non-metallic things as an alloy, like boron, an alloy of boron, or even alloy of other things which are slightly toxic. We could give uncertainties within 5%, and those are conservative. It was routine to get measurements that were within a few percent, and the branching fractions were necessary to get things on a scale. We looked a lot at different systematics. We want a sample to be optically thin. We could vary the beam intensity. Collisional quenching, was that important? We could throttle the pump. Is even quantum beats? Well, the laser's polarized, things start precessing, and so you have to be careful about stray magnetic fields. And so what you do is you zero the field when you can, and when the lifetime becomes too long, you have to zero it too well, you just spin it up real fast and average it out. And that's called the Zeeman beat. And the ultimate end-to-end test is periodic remeasurement of the benchmark lifetimes, where the theory was real good, or where there was very precise and different measurement technique. We could periodically measure those things and do a test of our whole experiment. So we had tight control over systematics. This is lifetimes from the University of Western Ontario or from UW, and there's a Gaussian there, and the lifetimes are literally within a few percent. They provide the absolute normalization that we want. So going beyond the lifetimes, you have to have good branching ratios. And for simple spectrum, you can calculate those. But for a more complex spectrum, when you get toward the bottom of the periodic table, where you have a lot of relativistic effects, you have a harder time, and you want to measure them. Well, we measured a lot of them using a Fourier transform spectrometer at Kitt Peak Observatory at the U.S. National Observatory, a big one. The multiply ionized iron group species don't persist. I was going to explain what a highly reliable line is. Well, it's a line, a UV line usually, that goes to the ground state or to a very low metastable state, and that's the real population reservoir. And so you get the right answer by almost by definition when you have these highly reliable lines. So those turn out to be very popular lines. We built our own spectrograph with cross dispersion. It's an SL, has a 22 group per millimeter grading, big grading. The Keck telescopes in Hawaii have gratings the size of the screen here, but they're mosaics. The diamond scribe wears out as you go across them. And so we ended up having about the same resolution as the Keck does. We had this out at the synchrotron for a while and then moved it back and built it into an SL with cross dispersion and a CCD array so that we could work in the UV. There's a kind of noise that shows up in Fourier transform spectra called multiplex noise, where the noise from the photon noise gets spread like peanut butter throughout the whole spectrum. And this doesn't have it. If you go to a dispersive spectrometer, it doesn't have multiplex noise. So we built a cross dispersive shell without multiplex noise for some of our work. We got our lab astro transition probabilities right because each one of them was individually normalized to radii lifetimes, and that made a big difference. And we had an edge over the competition in that we developed this universal atomine beam source. And we'd like to work in the infrared now. I don't know if I have a chance, but there is tunable infrared lasers technology available. So the mercury, cadmium, telluride, or Hawaii arrays have opened the infrared, and James Webb Space Telescope has these arrays, but no high resolution spectrometer. Now NASA has an infrared telescope facility on Mauna Kea, and that might do it. And they have mercury, cadmium, telluride arrays. And NASA's, well, I'll be long gone when they launch UVAR. It won't get launched until 2040 or sometime. But that's a UV optical infrared telescope, a big one they're going to launch. And in the future, people are working on it now. And the infrared is important because the interstellar dust is more transparent. and the galactic bulge is accessible. So the astronomers have this way of naming different windows where transmission's high, and the infrared's not completely opaque. There is bands and where the light can come through, and the H band is one of them. That apogee, the Apache Point Observatory Galactic Evolution Experiment is one of them. Okay, I haven't run out of time yet. I have a little bit of time. I want to talk a little bit about how the internet is going to work in the future and how entanglement can be understood. Now, I like to work with positronium. And when you make an atom out of a positron and an electron, you get, in most decays, you get two gamma rays of 511 keV. That's the rest mass of an electron, and they go in opposite directions. So you have a decay when they come together and annihilate each other, matter and antimatter. Now, the reason I like this is because all you have left is a vacuum. It's gone. That's all you have left. So it makes it easier to, even though you can't fit a 511 keV photon into a fiber, it makes it easier to think about it. How does this really work? Well, when this works, when an electron and a positron come together, annihilate, and produce these two photons, they're described with one wave function. They're entangled. These two photons go out in opposite directions with the same energy. If one of them is circularly polarized, the other one has to have the same circular polarization so that it cancels going opposite direction, so that you have zero angular momentum. You started with zero angular momentum, you got to end with zero angular momentum. So you end up with entangled photons that way. If one of these photons is vertically polarized, the other one has to be horizontally polarized. And it doesn't matter how far apart they are. It doesn't matter how far apart they are, they're entangled. So this is how the internet, this kind of idea of entanglement is how the internet will work in the future. This is a pure Bell state. Well, I've covered a lot of ground in 45 minutes, so let's go back to that and think a little bit more about it. You can't send a complete message using entangled photons. If you try, you would, but you can't send enough information to encode things, to encrypt things, to turn them into secrets. And so the Chinese did that. They jumped into the lead for a while in this post-quantum internet because they had a secure link, quantum secure link, going from China to Europe, to Austria. And how do they do that? Well, they got above the atmosphere. Fibers are too lossy for this to work. People are trying to figure out how to do this cheaply with fibers right now. If you could do it cheaply, you could go ahead and build the quantum internet. It costs a lot of money to put things even low Earth orbit. It's like $10,000 a pound, $25,000 a pound. So putting satellites is not the answer. But they use adaptive optics, and they had a secure link going to Europe. Now, why do they get so interested in this technology? Well, there's the infamous American Edward Snowden. Have you heard of him? The Chinese discovered the National Security Agency. This is according to Physics World, which is the UK version of Physics Today. They were listening in on everything that the Chinese said. They got mad about that. They didn't like that. Edward Snowden taught him that when he visited China, that they were listening in, and they got very interested in this technology. We believe that these entangled photons will provide a way to make the internet secure. Now, today, when you buy something from Amazon or some vendor, all you really have to encrypt is your credit card number, so you don't get extra charges on there. But it's done with something called the RSS algorithm, which is a public-private key system, which allows people to encrypt things using a public key, and then to unencrypt them, to decode them, you have to have the factors of the large number, and it turns out to be very hard. We're talking about a number that has hundreds of digits. Well, people think if you had a fully quantum computer, you would be able to do this very quickly and efficiently. And so we're going to go to an internet which uses this entanglement of photons to give us the security that we want. Now, we sort of know how to do it, but it's expensive. If we did it with satellites, it would be too expensive. So people are working on ways that are cheaper to build it. And there are tentative plans for building this post-quantum computing internet that will use entangled photons to provide security. They won't be gamma rays as they are here, but I just like it because there's nothing left after there's an annihilation, just the two photons which are entangled and going opposite directions. Okay, well we have plenty of time. I've gone fast and covered a lot of ground, but we have plenty of time for questions, and I'll try to explain things more thoroughly that you're most interested in. Yes?
I'm aware of RSS technology and how it's used today. And you have a device that's an RSS device and things. I had no idea that it was using a electron positron.
Oh, it isn't. It isn't. I gave this as an example of entangled photons.
Okay.
But they use photons. RSS uses visible photons, near-infrared photons.
Okay. So how is that technology actually capturing the positrons? In theory, how would that work? You're actually capturing the positrons to use in the entanglement to code.
Well, for this example, I use the positron just because there's only a vacuum left. There's nothing left.
So you're strictly using it as an example.
As an example,
Gotcha.
there's nothing left that will
Okay.
carry angular momentum. It's just a vacuum.
Okay, thank you. The other question I wanted to ask you is going back to when you were talking about the periodic table and the development, where the elements were developed, and it's always fascinating me, and how we make those determinations. When you have elements on the periodic table like mercury that could be developed, and according to the current theories, that could be developed in a large star or a supernova. How do you know that it's not all developed in a supernova? And
There's a mix. There's a mix.
But how do you know that the stuff that you think is coming out of the large stars isn't just a second generation star that developed something from a previous supernova?
Well, the previous supernova enriched the interstellar medium, and so it does end up putting material in the star. And stellar winds also can be very strong from AGB stars and can enrich the interstellar medium. So the material that shows up in the sun has a whole mix of different histories, and if you go to another star, you find different isotopes. It has different isotopes because it had different isotopic synthetic history.
Okay.
So each star has different isotopes.
I
I guess I was wondering how you determine that it originated with that large star rather than materials
Well-
from another star that formed into the large star.
There's clues that things were different at the beginning. You know, there's gamma ray burst,
Yes.
and people see those above the atmosphere. So some of those are neutron star mergers, and some of them are core collapse supernovas because they're different time scales.
Okay.
So things were different at the beginning. At the beginning, the stars were more massive, rapidly rotating and highly magnetized. So they were, in fact, different. Yeah, this is really just an example of entanglement of photons. But this idea of entanglement really uses the conservation laws as you get into it. You see the conservation laws appearing for energy and for linear momentum and for angular momentum. That appears in it. Those are good questions, by the way.
Thank you.
One thing that interests me about entanglement, you get a pair of entangled photons, so there must be a very interesting process to get enough signal to be able to measure the data from an individual photon, or is there a way to get a lot of photons that are kind of entangled in the same way, or how does that work?
Well, the fibers that we have today are too lossy. You can only send, and an entangled photon, you can only send it a couple kilometers. So that limits us. The fibers are too lossy. There's things being worked out to try to figure out how to make a quantum computing secure internet that has reasonable cost. But that's the challenge.
Yeah, thank you. Does anybody else have any questions for Jim? Well, thank you. Thank you so much, Jim. And on behalf of how about Terry? Is there some
Nothing yet.
nothing online? So, yeah, if we don't have any questions from the online audience, I'd very much like to present our guest this evening with a very special Madison Astronomical Society coffee mug
I'll enjoy this. We'll go to you.
as a token of our gratitude and appreciation.
Okay, thank you.
You're welcome, and thank you. So unless there aren't any further questions, I'd like to thank everyone for joining us for the August meeting of the Madison Astronomical Society. And we will see you all again at the next meeting. I'm trying to look through my notes. September 9th, thank you. September 9th, right here at 7 p.m.